Hi boys and girls, this is lecture 2.6 in Unit 2, the topic, infinite limits. A limit in which f of x increases or decreases without bound as x approaches c is called an infinite limit. Consider the function f of x equals 3 over x minus 2, another rational function, and by now we're aware that we should examine the denominator to determine if there are any values which should be excluded from the domain. We find that x cannot be 2 in this particular function. We would expect a vertical asymptote to show up in the graph. Of course, we see it here. And we ask this question, what is the limit of f of x as x approaches 2? To determine the answer to this question, we're going to look at the left hand and the right hand limits of this function. As x approaches 2 negatively, we can see that the function exhibits unbounded behavior toward negative infinity. Therefore, the limit as x approaches 2 negatively of 3 over x minus 2 is negative infinity. What about the right-hand limit? As x approaches 2 positively, we see that the function exhibits unbounded behavior toward positive infinity. Therefore, the right-hand limit, the limit as x approaches 2 positively of 3 over x minus 2, is positive infinity. The limit in general, of course, does not exist. This numeric data verifies what we have already seen. As we approach 2 from the left, we see the values getting larger and larger negatively. F of x is decreasing without bound. As we approach 2 from the right, we see that the function values are getting larger and larger positively. We see f of x increasing without bound. Just to clarify, an infinite limit does not mean that the limit is infinity. The equal sign in the statement, the limit of f of x equals infinity, does not mean that a limit exists. On the contrary, it tells you how the limit fails to exist by denoting the unbounded behavior of f of x as x approaches a. This terminology may seem confusing because when you see an equal sign in a statement, you think that it's stating that a limit exists and that the limit is infinity. However, when we say that a limit is infinity, we're saying that the function is unbounded at that point, and there is no limit where there is unbounded behavior. So in this case, this notation is simply a way to describe the unbounded behavior that is occurring at a certain point. It is not saying that the limit exists, and of course the limit cannot be infinity. When a function has an infinite limit, it is often the result of an asymptote occurring in the graph. We have seen several examples where the function has an asymptote. In the case illustrated here, both the right-hand limit and the left-hand limit, as the function is approaching a, is exhibiting unbounded behavior toward positive infinity. Thus, x equals a represents a vertical asymptote for the function. Let's determine the limit of this rational function as x approaches 2 and as x approaches negative 2. Of course, with a rational function, we need to closely examine the denominator to determine if there are going to be any domain issues. When we factor this denominator, we get these two factors, x plus 2 and x minus 2. Because of these factors, we will need to exclude 2 and negative 2 from the domain of this function. Furthermore, we will see discontinuities in the graph at 2 and negative 2. But they will be different kinds of discontinuities because of what's going to happen in the numerator of this function. It also factors into these two factors, x plus 4, x minus 2. Notice that one of the denominator factors cancels with one of the factors in the numerator, giving us a reduced rational function, x plus 4 over x plus 2. Now, just because we canceled this factor in the denominator doesn't mean that the function is no longer undefined at 2. It's still undefined there, and there is no function value there. In fact, it will still be discontinuous at 2, but it's going to be a removable discontinuity. There will be a hole in the graph at 2. Because the factor x plus 2 did not cancel in this function, there will be a non-removable discontinuity at -2. We'll see a vertical asymptote in the graph there. Now let's see if we can analytically determine the limit of this reduced function at the two values that were mentioned in the instructions, 2 and -2. Now that we have this reduced function, we're able to use direct substitution. Directly insert 2 into the x values in this function. We end up with 6 over 4, which is 3/2. Therefore, the limit of x plus 4 over x plus 2 as x approaches 2 is 3/2. Let's try to find the limit as x approaches -2 of our reduced function. X plus 4 over x plus 2. We still have a problem. There is still a vertical asymptote at -2. Therefore, this function, this limit, does not exist. Now let's look at the graph of the function to see if our conclusions are verified. And as you see, they are. At x equals 2, we see a hole in the graph, yet a limit exists there. The limit is 3/2. At x equals -2, we see a vertical asymptote, exactly what we expected. Unbounded behavior as we approach -2 from the left, unbounded behavior as we approach -2 from the right. The unbounded behavior, of course, indicating that a limit does not exist at -2. In this last example, we're once again asked to find a limit, and once again we have a rational function. We can see that the function is undefined at 1, and this is not going to factor in such a way that the x minus 1 is eliminated in the denominator. Yes, we can rewrite this function as x times x minus 3 over x minus 1, but the way the numerator factored did not really help us with our denominator issue. Not surprisingly, we're asked to find the limit at that value. We're asked to find the left-hand limit as x approaches 1 and the right-hand limit as x approaches 1. As you can see, analytically, there will be no rearranging of this function in such a way that we can use direct substitution. So we would need to depend on graphical or numerical methods to determine this limit, which is why I have this handy little graph right over here. As we approach 1 negatively, we see that the function is exhibiting unbounded behavior, tending toward positive infinity. Therefore, the limit as x approaches 1 negatively is positive infinity. Of course, it's not actually positive infinity. There is no limit here, but this notation allows us to describe the unbounded behavior that we see at this point. As we approach 1 positively, we see that the function is exhibiting unbounded behavior again, this time toward negative infinity. Therefore, the limit as x approaches 1 positively of our function is negative infinity. Once again, no limit exists at 1, but this notation allows us to describe the unbounded behavior that we see. That's the end of today's lecture, and I leave you with one more infinite limit to ponder. God bless you, boys and girls.